Like last time, we'll start with logistics, then a recap, and then focus on questions. And I did get a lot this time, which is awesome. So I will go through one by one. I'll start with questions y'all have who are here currently, and then pivot over to ones I got over email. So if you don't have questions at the moment, kind of think of what you might have as we go. But logistics wise, it's the same as the first exam. So you get a cheat sheet, whatever you want on one side of a sheet of paper. Doesn't matter to me. On the exam, you're provided an equation sheet. It's the same one that is on the practice exam packet. And the exam will be structured similarly. So it will be about 1/3 multiple choice conceptual questions by points. So meaning roughly 30 to 40 out of the 60 points are for multiple choice conceptual questions. And then the remainder is calculation. And they will pretty much just about all be of the style draw a free body diagram, find your net force, set equal to mass times acceleration, and solve for something. It will just be different scenarios. In chapter 5, it's primarily ones without friction or turning, so it's more focused on things like the normal force, weight, that sort of thing. In chapter 6, we add friction into the mix as well as something that can turn. And as we go through this, we'll see those examples again. It will be similar to the ones that are in the notes. I think that is it for the logistics side of this, other than that it is just chapter 5 and 6. Chapter 5 is where we first introduced what a force is. It's a push or a pull. And what really matters to make something move is the net force, what you get when you add all of the individual pushes and pulls on it together. You do that through vector addition. There is something else that limits the motion or how something's motion changes, and that's mass. So think of a lot of what happens in this chapter, especially as it relates to Newton's second law, as a fight between net force and mass. Depending on who's winning, different things can happen. Net force is what's trying to make something move or change how it's moving in some way. That could also mean slow down. Mass is what's limiting that change. And that is kind of the content of the second law. But anyway, the first law says, let's not even go that far. What if there was no net force? What happens in that case? And it turns out what happens is not much of anything. If there is no net force on an object, it continues doing whatever it was doing previously. If it was just sitting there, it'll keep sitting there. If it was moving, it'll keep moving in exactly the same way, which means in a straight line at a constant speed. It takes a force to speed something up, slow it down, or turn it. How much it speeds up, slows down, or turns when a net force is present is the content of the second law. It says that the size of that change, which is what we call acceleration, the change in motion of something, the size of it depends on how large the net force is. The larger the net force, the larger the acceleration. It also depends on how large the thing you're trying to move is. Depends on its mass. The larger that mass, the smaller the acceleration will be. It's harder to move bigger things. And the example I come back to a lot to see kind of all different facets of the second law is pushing a shopping cart around a grocery store. Because as you do so, you'll speed it up sometimes, you'll slow it down sometimes, you'll take turns sometimes. And you have to think about what makes it easy to do that, what makes it hard to do that. You'll probably notice as you add more groceries, it becomes harder to speed up the cart, becomes harder to slow it down, becomes harder to turn it. That's the mass right there. The bigger that number, the smaller the acceleration will be. The smaller the change in motion will be, unless you apply a larger net force to counteract that. So you will also notice if you do want to get the same sort of turns, the same sort of speeding up, the same sort of slowing down, you will have to push or pull or turn harder. You will need a larger net force on that shopping cart. So I would say if you do have to go shopping at some point, notice that. Notice all those different things that happen. But as we keep going with this, we need to be able to analyze things using these ideas. And in that case, it's easier to split things into X and Y motions, your components of both the forces and the accelerations. So you solve two equations, and depending on what you want to know, you solve them in different ways. The algebra just ends up a little bit different. Free body diagrams are a way of organizing your thoughts about the object you want to analyze. So you label all the forces acting on the object, and then you define some axes to split them into and focus separately on the x and y pieces. And then this solving process I'll come to here in just a minute after I cover the third law. So what distinguishes the third law from the first two is that it is about what happens between two different objects, two different things, whereas the first and second law are all about what's happening to this one thing. If there's no net force, what happens to this one thing? If there is a net force, what happens to this one thing? The third law connects that one thing to the outside world, to everything else around it. And what it says is, if that thing is pushing on something else, that something else is pushing it back on it. It also says if something is pushing on that thing is pushing back on that something else. There's always pairs of forces in every interaction between two objects. It also says more than that. It doesn't just say that the forces come in pairs, but that those forces will always be opposite in direction from each other and always equal in size to each other. And that's the hardest one to buy, is that the pairs of forces are always equal in size. But it is true in the sense that people have measured these forces on both sides of these interactions many times over in many different scenarios, and we've never found a case where that is not true. Okay, so as surprising as it feels, it is true. That's what I mean when I say it's true, it's not obvious. So a couple examples of that were, how does a car move? Well, the tires push back against the road as they rotate. In response, the road pushes forward on the tires. The only thing there is that makes it sound like tire pushes on road first and then road pushes on tire. That's not the case. The instant that the tires start rotating, the road pushes forward on them too. These things happen at the exact same time. There is no real first and second. And so action and reaction are bad terms to use here. They've just kind of stuck. So I think, can address one of the questions I got, which was, how do I know the order of the forces, which is which? The answer is there is no order. Either can be object A and either can be object B, and the law is still true. We just tend to pick one as object A because we think of it as sort of doing something and the other responding, but that's not actually, it doesn't have to be that way. That's just how our brains would like it to be. Similarly, on this last one, this is the most upsetting typically, is when Earth pulls on you, that gravitational force, you do pull back up on the Earth just as hard. The only thing is, Earth doesn't care. It's so massive. So we come back to the second law. This number right here is so gigantic that even though it feels the same force as you, its acceleration is barely anything. It does not change its motion in any observable way from that force. If something much bigger than you jumped over the Earth, quote unquote jumped, say the moon, Earth would notice. It would change its motion as a result. And in fact, as the moon orbits the Earth, Earth's motion is affected by that orbit of the moon as well. It turns out Earth actually, in some sense, orbits the moon as well. There's a point inside of the Earth that both of them circle around, and it's called the barycenter of the Earth. So that's a tangent, but just so you can see, like, Earth does move sometimes from other stuff. We know it from the sun, but even from the moon. There's a point somewhere about here, and that's actually what the moon's orbiting. It's also what the Earth is, the center of the Earth, orbits around. We just don't really notice that so much. Anyway, keep going. So that's the third law. It's that I push on you, you push back on me just as hard no matter what. As hard as that can be to buy sometimes. And then here is the most important page for all of the calculation questions in the entire exam. Because this is the process pretty much no matter what, even getting into chapter 6. The only thing that we add in chapter 6 is that for one, friction has its own equation, just like for weight we say is equal to mg. For friction, you say is equal to coefficient of friction times normal force. That's one new layer. For turning, the new layer is what the acceleration is. You can always write it as v squared over r in some direction, the positive or the negative direction. But all of that stuff happens after this, after number 4. In other words, every problem you do on this exam, and with Newton's laws in general, really, it's the same problem for the first 4 steps. Another way to phrase that still is don't worry what the problem is asking until you've done these 4 steps. If you haven't done them, what's it matter what the problem's asking? You haven't done enough work to know. So that's what I would suggest is sort of turn your brain off. Stop trying to answer the question immediately and just do this process first for every question. And it will probably, at the very least, get you a lot more partial credit. Okay, then we move on to different types of forces. So we talked about 4 different types: the gravitational force, tension, normal force, and friction. Gravitational, primarily for the exam, I'm just worried about this version of it, the one we've been using all the time, which is that on Earth, you can write weight as your mass times 9.8. It is true that if you go elsewhere in the universe, you have to take a step back to the universal law of gravitation, but not for this exam, other than technically it shows up for satellite orbits. So big G is needed to talk about finding the speed of a satellite in orbit around the Earth or something around the sun. And I'll get to that when I get to it. But anyway, that answers a couple things. One was a question about can you do questions with both the law of gravitation and Newton's second law? The answer is I can. I will not ask you one where it's like 2 planets acting on one person and you have to find the net gravitational force on them and you use the second law to figure out how they're going to move. It won't be something like that. If the gravitational force is involved, it'll be in the everyday sense. It will be in the sense of weight is mass times g. Another question, though, which is relevant for the satellite part of this is, what is the difference between big G and little g? Big G is a thing that tells you about the gravitational force between any 2 things in the universe. Any. With a technicality that they have to be point masses, concentrated masses, but if those 2 things can be treated like that, of just a little clump of mass, or a big one if it's spherical, as long as the 2 things can be treated like that, this law will tell you what the force of gravity is between them. Big G is the sort of conversion factor that takes you from measuring the masses of the 2 things and the distance between them to knowing what the force between them is. And it does have a specific value. It is a constant. Little g is something that is only relevant for Earth, at least when it has the value 9.8. So that is the value of little g. It's related to big G in that actually this right here is how you determine little g. It's big G times the mass of the thing you're interested in this case the Earth, over the square of the radius, meaning the distance between the center of the Earth and then wherever you're at. The only thing is, if you're anywhere close to the Earth's surface, and that can be within a few kilometers of the Earth's surface, you can go up kind of high, and this is still pretty close to true. Anywhere close to the Earth, that number you calculate will be about 9.8. It'll get smaller as you get farther away from the Earth, but not significantly until you're pretty darn far away from the Earth. So that's the difference between big G and little g. Big G is a universal number. It tells you about gravity everywhere. Little g is an Earth number. It tells you about gravity here. Tension, I don't think usually causes a lot of issues. It's just you pull on the rope pulls on whatever's on the other side of it. That's about it. Normal force is tricky sometimes. I'll come back to this question. I think someone asked something about it. I'll come back to that later. Normal force is trickier, for one, because I think people confuse normal force, Fn, with net force, which we usually say sigma F for. So normal force is the one that actually comes from different surfaces and keeps you from falling through them. Sigma F is what you get when you add every force on something together to say overall what happens to that thing. If you like, even though sigma actually means sum, think of it as an E. This is the effective force. This one is the force normal to a surface. Okay, so Fn can be one of the many forces contributing to sigma F, but they are not guaranteed to be the same thing. All right, a little bit more on that. Normal force, again, is what comes from surfaces that keeps you from falling through them. Often, especially if the surface we're talking about is the ground, that normal force will equal the weight of the thing. But that is not always true. And we can prove it by using a scale, which is measuring the normal force it feels on its surface from whatever's on top of it. So, even if something is on the ground, like a block on the ground, the moment you press down on that block with your hand, the reading on the scale is going to go up. It's not because the block weighs more all of a sudden. It's because there's another force in the vertical direction. Or if you tie a rope to the block and start pulling up on it, the reading on the scale, the normal force, will go down. Not because the block just lost weight, it's because there's another force acting in the vertical direction. So I phrase it as the normal force is just whatever it needs to be in order to balance out all the other forces present. Balance out could mean literally equilibrium, so the net force is zero. It could also mean the normal force is the thing doing the accelerating, doing the moving stuff up or down. That's what we see in an elevator. But that also means that you don't actually know the value of the normal force until you do this entire analysis to see what other forces are present, to see what kind of accelerations are happening. So it is not one that has just a definite equation like weight does. Weight is mg always. Normal force is whatever it needs to be. All right, and then similar to that, someone asked about the elevator. I'll come back to that when I get to questions. Someone asked about this one. I'll get back to that with questions. I won't ask questions about systems on this exam. You won't have to do it for more than one object on this exam. That you tend to see more in dynamics if you take it. That was just so I've actually told you that it's a thing that you can do. Chapter 6. Friction really could have gone at the end of the last chapter. It just would have been a little unbalanced in terms of the length of the chapters, because it's just another force that can act on stuff. It comes up when one thing's trying to slide across another. And I say trying to because depending on whether sliding is actually happening or not, you're dealing with two different kinds of friction. If they are not sliding, but you are trying to make something slide by pushing on it, that is static friction. That is the grip on the surface that is not letting you move the thing very easily. I come back to like a couch. You're trying to move a heavy couch. It's hard to do. It's hard to get it moving at first, and it's because static friction is fighting you. But if you push hard enough, eventually you win. You beat out static friction and you get the couch sliding. So what you did is you pushed harder and harder until you overcame the maximum static friction that can exist between the couch and the floor. Once you push harder than that, friction just kind of sucks. It gives way and it becomes kinetic friction. That's the kind we talk about when something's sliding. So kinetic, it's a fancy word for sliding friction. And it is always weaker than static friction because friction comes from bonds forming between two surfaces. It's easiest for those bonds to form if you leave the two surfaces alone. If you let them sit, the bonds gradually form over time. So time actually is a factor in friction. It's just one of many that we don't account for in this kind of basic model of friction that we've talked about. So this is like a first pass at how friction works that we've discussed in class. If we are dealing with either sliding friction or just that most static friction you can get the maximum, we do have something like weight is mg. It's just for friction, friction is coefficient times normal force, or kinetic is coefficient times normal force, just a different coefficient. If we're not at that point of either it's about to give way, so like right at the verge of sliding, or it actually is sliding, we're in this realm where friction is kind of whatever it needs to be to balance out the other forces on the object. So friction can sort of be like the normal force in that way. It's whatever it needs to be, and it will be that way up until you reach the maximum value. At that point, it'll be like, nope, I'm done. I'm not changing with the force anymore. This is the most I'm going to do, is the maximum static friction value. And once you hit that point and beyond, so for sliding, it is more like weight, where it has a definite expression. That is confusing, but that's one of many reasons why friction is hard. Okay, someone asked about the kinematic equation on this one, so I will come back to that a little bit later. All right, circular motion. This is us recognizing that we have no idea what happens if something is turning. We've spent so much time, we've spent 5.5 chapters about things moving more or less in a straight line, or at least not rotating. So for projectile motion, it's not a straight line, but we didn't talk about the fact that when you throw a ball, it can spin too. And in fact, even this does not fully cover that. Isn't physics fun that way, about how you talk for so long about so little? But that's because that's how this stuff works. Anyway, uniform circular motion is circular motion at constant speed, meaning you're taking a turn in your car at 20 miles per hour throughout the entire turn. You don't speed up as you go through it. You don't brake as you go through it. This is only able to talk about turns like that. We will talk about those kinds of turns later, speeding up while turning or slowing down while turning. But this is not that. This is just turning. In that case, your car is still accelerating because its velocity is changing. The direction it's going is changing. If it were not accelerating, it would keep going straight. That's what your car wants to do. Its inertia says, keep going straight. Something's making it do this instead, making it turn. So we call that act of turning, we call the fact that it's constantly changing its velocity a centripetal acceleration. And it's because instead of going the way the car would like to, off in a straight line, something keeps kicking it back towards the center, making it stay on a circle instead. And over here, you can kind of imagine, the car's like a kid wanting to walk around a store, and the centripetal acceleration is the mom with a leash. Yanks the kid back towards, if it's that kind of mom, yanks the kid back towards wherever she's going. In this case, she wants to go in a circle. The actual thing doing the yanking, the actual force that does it, we call the centripetal force. In this case, he literally is the one pulling. He's like the mom. Here's the leash. Here's the kid that wants to go this way, but you're making him go in a circle instead with that centripetal force. We first found how big that acceleration is for something moving at a particular speed and a particular radius. Reason those two things matter is it's harder to keep something moving in a circle if it's going really fast. It's also harder to keep it moving in a circle if it's a really narrow radius, really small radius, because you have to yank on the thing even harder to let it keep going in a turn instead of going straight. I come back to cars again. What is harder? What is scarier, more dangerous? Taking a turn at 80 miles per hour or 10? It's because you need a larger centripetal force to let you take an 80 mile per hour turn, because you need a larger centripetal acceleration, a larger change in your velocity. Is it scarier to take a turn that is like a huge roundabout where you have forever to turn your wheel? Or is it where you're coming up on a parking lot and someone left you no room to turn in and you got to tweak the wheel as hard as possible? It's because of that radius, that smaller radius, that is harder. You need a larger centripetal acceleration. You need more force from the ground to be able to do that. And that's all covered here. And then also here for what provides that acceleration, whatever force is acting to do it. It can be one of many types. It can be from a rope. It can be from the earth itself or any other object. It can be from sliding on something. It can be friction. It can be from not falling through a surface. Part of that force can act to let you take a turn, a normal force. The rest of the chapter is pretty much just going through all those different scenarios. You won't need to know about the centrifugal force, the one we talk about here, because again, it's not real. It's not something actually pulling you outward away from the turn. It is what happens when there's not enough stuff pulling you inward towards the center of the turn. It's like up here. If we come back to the kid on a leash, if he's running too fast, the mom can't hold on. So where does he go? Away from the circle towards the outside of the turn. Not because something's compelling him or pushing him away from the center of the circle, but he just wants to go that way. His inertia, or in that case, his innate desire to run off in some other direction, is what makes him go that way. But from the perspective of the one doing the turning, so you in your car, it sure feels like it. Sure feels like something's making you go that way. But what it actually is your body just likes to go in straight lines, wants to do that due to its inertia, and you really have no say in the matter. So centrifugal force is not real in the sense that it's actually just you don't have enough centripetal force to do the turn you want to do. Okay, then we looked at the gravity case. I will ask, or I am likely to ask a question that is pretty plug and chug. I give you enough information to put into this to tell me the speed of an orbit. The only gotcha there is like the one we got to with this question, which was you need to know the radius of the orbit. But radius is how far away the object is from the center of the Earth. That's what you're orbiting around. If I give you the technical term is the altitude of the satellite, but how far it is from the surface, and then I give you the Earth's radius, you need to put those together to get how far the satellite is from the Earth's center. And that's what we did over here. We added them. I won't ask about orbital period, so this goes away too. It's just neat that it works. I will likely ask one of this style. Could be about friction, could be about other stuff. But again, the math, the procedure is more or less the same, except for, let's see. If I drew a dividing line between what's exactly the same as in chapter 5 and what's new, it would be all the stuff on the right is this chapter, but everything up until then is the previous chapter, other than, I guess, just knowing how to label friction. So it's the same procedure. You just add the layers of, for friction, you have this special rule, if it's maximum, and for turning, you have this special rule. But they're just an extra rule that you apply at the end of the problem. They're not a brand new scenario. And banked curves are just the last kind of force or centripetal force we will talk about, is just provided by one piece of the normal force. So if you're on a banked curve, you don't need friction to be able to take the turn. It does help, but it is not required as long as you go at the appropriate speed that the turn is designed for. So I think of this as normal force lets you take it if you go exactly at speed v. Friction is what gives you wiggle room. So what you see in real life when you drive over like a flyover, you don't have to drive at exactly 50 miles per hour. You can drive at a range. But if you go too slow, if you go like 10, you will see yourself start to skid down that flyover if you don't have enough friction on your tires, at least. Or if you drive too fast, you will shoot off it and, rip. But anyway, that is, I think, a recap of everything. So are there any questions from the folks that are here currently?
One more small question,
Yeah.
Is the maximum static force constant or is it variable?
It is a little bit of both, I guess. So it is defined to be, or at least, this empirical law says it depends on the two materials at play and the normal force. The two materials are pretty hard to change mid-scenario, like mid something's driving over something else, but the normal force could change in principle. Like if you're driving, you're taking a turn, and a bird lands on your car, all of a sudden the normal force on your car is slightly higher because you're being pulled down more. The surface has to push up more to keep you from falling through. And so technically that bird sitting on top of your car increases how much friction there is on the car's tires. Maybe not much, but I'm just saying, like, it's variable in the sense that it can change in reality. I will not ask you a question where it does change mid-scenario.
Yeah, I was going to say, you did a really quick demonstration the other day when you were doing friction force on a ramp.
Yes.
How does it change like as it angles? Because I didn't really understand how that's any different from. I felt like it was just a free body diagram, like tilted up a little bit. I didn't feel like it changed that much, but I kind of know it has to. Like I did an example problem and I got it wrong. So
So as in like how the normal force changes?
and just the friction does the friction change at all? I'm not sure which part
Oh,
of it I got. It was
okay.
the
Yeah. So the most friction you're gonna get, yes. The coefficient of friction is just a description of two materials. That one doesn't change with the angle. But this one, the maximum overall frictional force that you can get, it does change as the angle increases because the normal force changes as the angle increases. It gets smaller, so the most friction you can get out of that surface does get smaller the steeper the surface is. A real life everyday example of this is it's one thing to walk on ice on flat ground. Like it's a little sketchy, but you can get some grip. If you try and do it on something that's a 50-degree slope, even though it's the same ice and it's the same shoes you're wearing, the same two surfaces, so this number's the same, this number is dramatically smaller on that surface. And so the maximum friction you can get out of that surface is smaller.
Can you explain the question for question 5 on the guided practice chapter 6?
Question 5. Okay. Yeah, this is one someone else asked about too. Yeah, I'll go through this. All right, and it said the coefficient of friction, static friction between Teflon and scrambled eggs is 0.052. What's the smallest angle? So that's all we're given. And that makes it feel like, what? You can do that? They ask, what is the smallest angle at which the scrambled eggs will start to slide? And so I'm going to go ahead and say, okay, so this is going to be where the eggs are at an angle. And really, it's a pan, and then the eggs are, I guess it's going to be green eggs. They're on there. But this is just like any object on a ramp as far as how you would analyze it. So I'll just simplify down to ball on a ramp. If the coefficient of friction between that ball and the ramp surface is 0.052, what's the smallest angle theta at which this ball will start to roll down or slide down? So I need to know the forces on the ball. It'll be its weight. It'll be normal force. And then if it is trying to slide down, friction is what keeps it from doing so up into a point. It asks at which angle it will start to slide down, which means if I keep tilting the pan up, starting from with it flat, there will come a point where the friction can't keep up with what's pulling the eggs down the pan, which is one component, this part of their weight. So I'll label that better in a minute. But the amount of friction needed to keep the eggs from sliding grows, but the max that you can get out of the surface shrinks. So it is not able to keep the eggs from sliding down. So this would be the maximum static friction. That's the most you're going to get before the eggs suddenly do slide. If you tilt to any angle other than this particular angle, so you tilt it just a tiny bit more, the eggs will slide. So this is really asking, in a way, what is the maximum static friction you can get out of this surface? But if none of that was clear or made any sense, it's still the same procedure. We still just label all our forces and go through and see what happens. So I will turn this into a free body diagram. And to do so, my eggs become a dot. I guess I'll use green. Here's my normal force from the pan surface. Here's the weight pulling down on the eggs. And then here is friction, what's doing its best to keep them from sliding.
Static friction?
Yes, it's static because it's asking, like, what's the angle at which if you tip it any more than that, the eggs will slide. This is the most friction you're going to get before that happens, the maximum possible value. So this is right at that tipping point.
Don't need the normal force and the static friction to get the
Yeah, but see what you're doing is
wait.
you're trying to solve the whole problem at once, right?
Mm-hmm.
That's what I'm suggesting is don't. Just go through the motions. Do the same steps that we do no matter what problem it is, and the answer will fall out for you.
Oh, okay.
Yeah.
Thank
So
you.
that's what I'm going to do is I don't know the answer. I do because I've done this type of problem many times before, but like if it's the first time I'm approaching this, I don't know. So I'm just going to do the procedure I know to do and see where it gets me. So my next thing is I need axes. I'm going to choose the most convenient ones, which is where I don't need lots of different components. So it will be that this, I'll call the Y direction, and then I'm going to make this a little bit more perpendicular because static friction, or friction in general, and normal force are always perpendicular to each other because they're meant to be. They're two parts of one force. And then I'll choose along the pan as the x-axis. And this is another one where there's a couple questions about like, how do I know whether I choose this way or that way as x? Like, should I call this positive x or should I call this positive x? And the answer is it doesn't matter. It does not make a lick of difference in the final answer. What it does do is every time you label a force on the x-axis, you've got to decide, well, if my positive x is this way, I would call static friction negative in this picture. If positive x is this way, I would call it positive. And same goes for any other vector along the x-axis or even components of vectors, so like the component of the weight along the x-axis. And then same goes for accelerations. So if you found that the eggs accelerate down the ramp, they speed up and as they slide, with these axes, you'd be like, oh, great, positive acceleration. With these axes, you'd be like, oh, negative acceleration. But remember, negative alone does not mean speeding up or slowing down. That's from way back. Negative means for acceleration, I don't know until I know the velocity as well. If they agree, if the signs agree, speed up. If the signs disagree, slow down. And that is all that matters. It could be that both are called a plus, a positive velocity, a positive acceleration, but just as well they could both be called a minus. So anyway, that's addressing a question someone else had asked. But okay, so we've labeled our free body diagram. I'm going to choose down the ramp as my x because it's kind of more like what we're used to. But again, it's a choice. I could have done it the other way. And I need to get my components. So I've got normal force, I've got weight, I've got that static friction. And this is a tip for static or knowing when it's maximum because it's not like it takes some learning to get used to knowing when. If they're trying to tell you is on the verge of doing something, like just before it slides, or is about to skid, or like something's about to happen, that's a maximum value for the static friction because it is the dividing line between one behavior and another, between static friction of some value and then between kinetic friction. It is the thing that draws the line in the sand. So if something's on the verge of happening, on the verge of sliding, you know you're dealing with maximum static friction. But I'm going to use those to find my net force. All right, so normal force has no x component with the axes I've drawn. It points in the positive y direction. Weight I'll come back to so I can label its components, but then static friction, it is, let's see, 0 in the y and then negative in the x direction using the axes I chose. All right, for weight, I need to split it into two pieces. One is going to be along the y direction and one will be along the x direction. But if I'm going to do that, I need angles to work with. We've been through this a couple times, but if I go through the geometry, for whatever ramp angle this angle will also be that same 1. So the angle between the weight vector and the normal force direction, the normal force axis, is that same angle. So for the y component of the weight, it's this one right here. Since it's touching the angle theta, it is weight times cosine of theta. And it's negative because it's downward along the negative y direction. And then this one is positive w sine theta. All right. The x, we already said, is w sine theta, but weight is mg, and we typically end up using it that way. So I'll go ahead and write it like that in the positive direction. And then for the y component, it is negative mg cosine theta. From there, I find my net force in each direction. So mg sine theta minus fs max, and then Fn minus mg cosine theta. So my net force in the x direction is the first box. My net force in the y direction is the second box. I'm guaranteed by Newton's second law, I can always set those equal to mass times acceleration. And now I need to decide, is it accelerating or not? Well, I come back to the problem statement. It says, what is the smallest angle from the horizontal that will cause the eggs to slide across the bottom of a Teflon-coated skillet? I'm going to say that this is poor wording, and I should have added it as a hint now that I read it, because this is really going to be the smallest angle at which, if you tip any beyond this angle, that is when the eggs will start to slide. This is the cutover point. It's the dividing line where if, say this angle comes out to, well, it gives the answer right here, 2.98 degrees. That means if you tilt the pan to 2.9800000001 degrees, the eggs will slide, but they won't at 2.98 degrees. That's the problem I have with the wording, is it's not the smallest angle that will cause, it's the smallest angle just before the eggs slide. And that's why I know that the x acceleration actually is 0 here, because the eggs will be at rest at this angle. They just won't be the moment you tilt beyond it. The y acceleration is 0 because the eggs are not flying off of the surface of the pan. So I've got these two equations. Mg sine theta is equal to Fs max. Because if the whole right-hand side is 0, I can just move the negative stuff over to the other side. Same here. All right, so I've got those two to work with. And now is about where I would start wondering what I'm trying to find. And I'm trying to find that angle theta. So if I try and do that, I might start by saying, well, I can solve for sine of theta. If only I knew the mass of the eggs or the static frictional force, but I don't know either, so that sucks. So I start grasping at straws. I say, what else can I do here? Well, maximum static friction can always be written as coefficient of friction times the normal force. I don't know if that helps me, but it's true. And so I look at this and say, well, maybe that is a little better because they gave us the coefficient of static friction. But I don't know the normal force, and I don't know the mass. But wait, yeah, I do. At least the normal force part of this, I have another expression for it, and I can put that in here. So I'm just going to rewrite a little bit. Sine theta is coefficient of friction times, I can now put that thing in for Fn, mg cosine theta over mg. But look, mass cancels out. I didn't need to know it. Yay. Even g cancels out. I know it, but it cancels out. So now I'm at sine theta is equal to coefficient of friction times cosine theta. I need to solve this for theta. Well, sine over cosine, if I divide both sides by cosine, is tangent theta. That equals the coefficient of static friction. Or theta itself is the inverse tangent of the coefficient of static friction. So it's the inverse tangent of this number right here. Done. But I had no clue that that's how I do it until I got to about here. Like, I just went through the motions of the problem. I went through the same steps I do for every Newton's Laws problem ever in the universe. And only then, once I got that far, did I start worrying about what to do, because it's the same up until that point. It's at this point where you do kind of need a couple strokes of genius, quote unquote, but this is still pretty far into the problem before you even have to worry about it. And that's how you get a bunch of partial credit. You may not make it through the whole thing, but at least you got this far. If you try and figure out the whole problem at once, you'll get stuck. You'll write half of a letter, then say, oh, I don't know, and then skip it. You say you'll come back later, and then you run out of time, and now it's a blank page with 0 points. So don't. Just do the partial credit stuff. Do the steps all the way up until that point, and then worry about the problem.
Could you
Yes,
show
a
a
lot.
free body diagram example?
Yes. Okay, so any particular kind of scenario you want a free body diagram for?
No.
Okay.
No, just random.
Well, let me do one on a flat surface since we just did something on an incline. So we'll do, because I think I mentioned this at one point as like a half joke. I don't know, someone's dragging a log. I'll just add that into the mix. But there's a frog on it. Oh no, what have I done? Anyway, that, and then there's like a bird sitting on top of it. And I don't know, the list goes on. But it's just some random scenario. And I'm asking what's going to happen to maybe the log in this situation. Well, and this, I picked this one also to address a couple questions at once, I think. To answer that, to figure out what forces are acting on the log, just answer what is it interacting with. And for the most part, that really means what's it touching? It's touching the ground, that's one thing. It's touching a rope, it's touching a frog. It's not touching the bird, so who cares what's happening with the bird? But there is one that is sort of a gotcha. It is not touching the entire earth in the sense that, like, all of it's in contact, and yet the weight that the log feels is coming from the earth, and it would, even if you lifted the log up off the ground, the earth would still pull on it even though it's not touching it anymore. So that's the one that's not just touching, is weight. But it's also the one that you know anyway. You know you label the weight here. So the weight is one force on the log. There's tension from the rope pulling on it. I know it's along the rope because that's how ropes pull, is along their length. I know it's to the right because you can't push with a rope. And for the frog, it is sitting on the surface. This is one where I have to maybe invoke third law. The log's pushing up on the frog is going to be pushing back down on the log. If you want, it's the force of the frog on the log. But it is technically a normal force. It is something that is acting perpendicular to those two surfaces. Surfaces meaning the log surface and then the frog's feet. All right, we could also ask, are we just starting to yank this log? Because in that case, it's going to start to slide, and yet the frog is not going to immediately slide with it. It has some inertia. So, as the log gets pulled to the right, it will pull on the frog. The frog will exert, by Newton's third law, a force backward on the log. This is another force. It's the frictional force of the frog on the log. But that's only going to be there up until the frog starts to slide with the log, they have the same speed. In that case, nothing's trying to slide across anything else. This only happens when there's a mismatch in speeds. That's getting deep in the weeds. I never taught you that. I know. But I'm just saying, like, I'm just looking at the things that are touching, things that are interacting. And if I don't know the direction of a force, I use Newton's third law to figure it out. If I turn this into a free body diagram, because I've labeled everything, well, almost everything, I am missing one thing. The ground surface provides a normal force to the log. And the ground surface, if I'm pulling the log to the right, is going to try and keep it from sliding to the right. So there is that frictional force of the kinetic kind if the log is sliding to the left. Now it's just a matter of moving all of that over to my free body diagram. So we got weight, normal force, tension, the friction from the ground, the friction from the frog, the normal force from the frog, and I think that's everything. And from here, I would break things into components. They already all are in X and Y directions. And find the net force, and then find whatever it is I want to know about. Now, that may mean I have Fn equals a whole bunch of other stuff I don't know about, but that's because that's real life. You don't always know every given that, or you're not always given everything that you need to know to solve a problem. Sometimes you got to make a measurement. You got to figure some of this out in a different way. But in a physics class, in a, contrived thing where everything has an answer, of course, you're given all the stuff you need to be able to solve for whatever they're asking for. And that actually makes it easier to do because there must be a solution. You just got to find it. All right, other questions? Okay, if not, I'm going to try and start chipping away at the ones I got over email. I got a lot, which again is exactly what I want. It will take a little bit to get through them, but that is also fine. Okay, and I tried to sort them, kind of get them in order, but we'll see how well I did. Can you give an example or two that are kind of related to the picture of someone jumping over a hole in the ground? How would the force vector of you on Earth be presented in a different problem? So, yeah, this was that one where you got a guy jumping over, and I said, yeah, the Earth pulls on you. We all know that. But the third law says you also pull on the Earth. So if you're wondering, like, why or when would that be relevant, the fact that the Earth is being pulled on, it would be relevant in a strict sense if I just ask you, what's the Earth up to? How does it move? You would have to account for that force and also every other human being on Earth pressing on it and all the other things touching it. The nice thing for us, if we do really want to answer what's happening to the Earth, is most of that is such a tiny force that who cares? What really matters is that the sun pulls on the Earth. That's the strongest of those many, many forces. Why? Because the sun is ginormous and the Earth is ginormous. That gravitational force between them is going to outweigh, in a literal sense, anything else involved. So, I guess my short answer is, like, if you wanted to know about the force, the acceleration of the Earth, how it's going to move in the next moment, how its motion will change, you could do the same procedure. And this force you exert on the Earth would be one of billions of other forces in this list. But what you'll find is we also have the force the sun exerts on the Earth as one of those in this list. And if we actually calculated these numbers that go here, these will be some kind of number, and then the number for the sun on the Earth will be eye-popping with how large it is. It's just a huge, like, it's, why even care about the other numbers? They're so small compared to it that it makes barely any difference. And that is why the motion of the Earth through the solar system is primarily dictated by the sun. Or you could say it's because only external forces are what affect the motion of an object. You need things outside of the system. If you take the system to mean the Earth plus everything on it, then it really is only the sun that's relevant. But if you want to consider how does Earth move relative to the people, then you would technically consider all of these forces too. All right, that's the first question. Number 2, how am I supposed to determine the order of the force an object exerts on another, or reaction force? How would I know if I have the correct reaction force? So for the first part, the order, we talked about that. It doesn't matter. Doesn't matter which you call action or reaction, because there is nothing that comes first. They happen at the same time. But how would you know if you have the correct one is because the third law is deceptively simple. It's simple once you buy it, but up until then, it doesn't feel right to do. What I mean by that is pick any force you're familiar with. The normal force on something. All right? What really is the normal force? It's the force that that surface provides on this, I guess we'll do the phone, since that was brought up a little bit later. So this is a phone sitting on a desk, maybe. The normal force is the force the surface exerts on the phone. Third law says there is another force. And all I do to figure out what it is reverse these. B on A instead of A on B. So there is a force that the phone exerts on the surface. And the third law even tells me which way it points, in the opposite direction, and is of equal size. So there is the force the phone exerts on the surface. Here is where I need to ask, but why? The third law guarantees it exists, but it doesn't explain where it comes from. Where it comes from is the phone doesn't want the table going through it either. You know, the table keeps the phone from falling through, but the phone doesn't want the table to phase through it. So it provides a force preventing the table from doing that. In some weird sense, if you do this kind of balancing of forces, the phone just as well keeps the table from flying up. I think that answers the question of how do I know if I have the correct reaction force? Because all you do to find it is B on A. It mentions one of the forces have to do with Earth, with the exam also mentioned weight, for example. Yeah, weight is a general purpose statement of force Earth exerts on a thing. So it would be force E on other thing. The reaction force automatically is force other thing exerts on E, on Earth. And so if you're okay with just swapping two letters, then you know how to apply the third law. It's just that it doesn't feel right at first to do that. To say a little bit more about that for the phone, there is another force acting on it. This we just talked about what the table does to it, but Earth is also pulling down on it. This is the force of the Earth on the phone. The third law does not care about these two, even though it feels like they should be a pair. Third law has nothing to say about that because these are both forces on one thing, on the phone. The third law is about forces between two different things, in this case, the Earth and the phone. The reaction to that one is that the phone pulls on the Earth. Somewhere down here, somewhere just through the center of the Earth. And that will affect the Earth's motion, not the phone's. So this is a third law pair. This is a third law pair. These two are not a third law pair. They're both on the phone. They are equal and opposite. I'm not denying that part. They're just not equal and opposite because the third law says so. They're equal and opposite because the first law says so. The phone is just sitting there, so the forces on it must balance. The net force must be 0. That's the first law, not the third. All right, we're through question 2 of 21, I think. I'll try and speed it up a little bit. Number 3, quiz 5, question about the phone. Okay, I just covered that, so we're good on that. What's the difference between little g and big G? So we said little g is a thing about the Earth and what it pulls or how strongly it pulls on you. Big G is a universal constant that can tell you how strong anything pulls on anything. And we found that little g is related to big G. It's big G times the mass of the thing providing this gravitational force over the square of the distance between it and the other object that's pulling on. You don't need to know that for the exam. This is not important to know for the sake of the exam. I'm just telling you why you have these two seemingly similar numbers that do different things. The one over here is the 9.8 number. The big G one is the 6.67 times 10 to the negative 11 number. It will again come up for satellite questions, but just as a number that you can look at on that first page with the like constants that I give and put it into that equation. That's the only way in which you need to know about it for the exam. Could you go over the wording with forces on forces? So graded practice, chapter 5. So that's what I copied here. So it's the crate on the cargo ship. And the questions were, which is blurry because I had to make them tiny, which of the following is the Newton's third law partner for, I believe that's Fn. So Fn in this case would be the normal force provided by the surface here. That would be the force the deck exerts on the crate. The reaction to that is the force the crate exerts on the deck. You just reverse the order. I do, after seeing someone come by with this one, I guess I didn't realize how like funky the notation is. That says F deck, comma crate, but that is meant to be the force the crate exerts on the deck. So it's the force on the deck due to the crate is I guess how I would read that out loud. But I don't like that notation. I try and be more explicit like this. Or I say like, so that's the first one. Which of the lettered arrows represents the force? Again, I'm going to read this as on the earth due to the crate. Well, the earth pulls the crate down, so the crate pulls the earth up. That's why it's C. Which is the force on the deck due to the crate? So what does on the deck due to the crate is going to be down, or well, technically at this angle, like we said. And that was arrow E. The force on the crate due to the deck is the third law reaction there. It's B. And then which represents the force on the bumper due to the crate? The crate is smacking into the bumper, or you could view that as the bumper is pushing on the crate so it doesn't slide off the boat. So the crate pushes on the bumper this way, the bumper pushes on the crate the exact opposite way. And the question is about the force on the bumper due to the crate. That's arrow A. So the force on the bumper due to the crate. All right, I think that's that question. All right, what is your thought process in identifying the forces being applied to an object alongside determining the orientation when drawing the free body diagram? So I talked through that a little bit with the frog on a log thing. What I do is I say, what's it touching? If it's touching something, there's a force, at least one from that thing. A lot of times there's two, because you have the friction and the normal force, and you just think about them as two separate pieces. As far as the orientation of the forces, each one kind of has a rule. So for weight, it's just down. For tension, it's along the rope. And it's in the pulling direction. You can't push something with a rope. For normal force, it's not that it's always up. You see that happen so often that you think that's the rule. It's not that it always points up. It's always perpendicular to whatever surface is providing it. If that surface is tilted, so is the normal force. We see that with the ramps. The normal force is still perpendicular. That's what normal means. Even though, say, weight is straight down. All right, so just perpendicular is all that one is. And then friction. And then I guess I'd say more about, well, why is it that way and not this way? Because it is there to keep stuff from falling through the surface. So which way would the thing fall if it weren't there? In that case, it pushes back and says, no, you can't go that way. Friction is always parallel to the surface providing it. So in this case, if you've got a box on this ramp, the normal force is, as I said, but then the friction, it actually could be either way. It could be up the ramp, it could be down the ramp, one of those two. To decide which is which, it's a similar question. You say, which way would it slide if friction weren't there? If I made this surface totally icy, what would the thing do? And then you have to rely on sort of your own common sense. Friction says no to that. It says, I don't want you to slide that way. I oppose it. And so it acts in the opposite direction. If there's enough forces trying to pull the box down the ramp, that means friction will say, I don't like that. Pulls up. If there's enough stuff trying to pull the box up the ramp to either try and make it do that, or it actually is doing that, actually is sliding up the ramp, friction says, don't like it. Other way. It's always trying to prevent sliding. All right, a few questions on universal gravitation, second law. So I had mentioned I won't do something over universal gravitation. It'll just be weight is mg. Re-explain the man in the elevator question from the chapter 5 notes. I will do that. Okay, so the actual free body diagram we already did. The idea is not that you don't do one for this. We just did on the previous page. And what we found is, what's he interacting with? Just the ground. That's the only thing he's touching. He's also not trying to slide across it. He's just standing still. Nothing's pushing him to the right or left for friction to be like, I don't like that. So there is no friction on him right now. There's only a normal force keeping him from falling through the floor of the elevator. And then the weight from the earth is always pulling down on you. So those are our only two forces. We said, therefore, that the net force in the y direction is the difference between them, since they point in opposite directions. That's equal to the mass times the y acceleration, because second law says always that's the case. And then what I did is said, okay, so the normal force itself is equal to weight plus may, if I just move weight to the other side. Reason I cared there was Fn is actually what a scale is telling you. In the case where the acceleration is nothing, you're just standing there, or you're moving at a steady speed in an elevator, then the scale will not lie to you. It will actually tell you a number that is the same as your weight. But it's not like it's built to only do that. There's not a device you can make that will only tell you the gravitational pull from the Earth if it's a scale of some sort. All it's doing is saying, how hard are you pressing on my surface? If the only thing happening is you're just standing there, the only thing making you press into it is your own weight. That's why they end up equal. Anyway, long story short, that scale reading can be very different from the weight. If the acceleration is positive, it will be bigger. If the acceleration is negative, it will be smaller. If the acceleration is 0, and only then will they be equal to each other. And so the cases we went through are a positive acceleration, meaning upward, a downward acceleration, and no acceleration, because it's moving at a constant speed and not turning, now that we know that that contributes to accelerations. From there, it's kind of just put the numbers in. I don't think I have much to add for that, but it's positive acceleration can mean you're starting to move upward because you weren't moving and now you're going up. You had a positive acceleration to give you that kick upward. It could also mean you were moving down and you needed to stop. You still need an upward sort of kick to be able to do that. And that's going to come from the floor of the elevator. It's what brings your body to a stop as you come to your floor if you're going down a floor. And then the negative acceleration is vice versa. So if you're starting to move downward from a stop, or if you are moving upward and coming to a stop. Graded practice, chapter 5, question 9. Force is downward. How? Since there's a normal force canceling out the negative weight, meaning the tension should be the only one causing a force, and it is up. All right. A block weighing 3 newtons is at rest on a horizontal surface. A 1 newton force is applied by means of an attached vertical string. So I'll just go ahead and start sketching that. All right, I'm not going to look at what the question's asking for a second because I can already do some stuff here. I can say weight is down. It said tension, the rope is pulling upward. It's sitting on a surface, so there's an upward normal force. Keeps it from falling through that surface. It's not trying to slide left or right. There's nothing trying to make it do so, so there's no need for friction to oppose that. So friction is not present. And let me come to what it's asking. 1 Newton upward force, or the magnitude and direction of the force of the block on the horizontal surface. That's the trick. It says of the block on the horizontal surface, not the force of the horizontal surface on the block. So normal force, another way of phrasing it is the force of the surface on the block. Friction also is a force from the surface on the block. It's just side to side. And we said, it's not present in this problem. All right, what's the reaction to that? It's the force of the block on the surface. How would I find that one? Well, it's got to be equal in size and opposite in direction to this one by the third law. So if I just found the normal force for this problem, I would be done. I just have to remember that this force, which it's asking about, points in the opposite direction, so downward. So that might be the confusion, is you found the normal force correctly, but then you answered for its direction, not the direction of the force of the block on the surface. And, I kind of picked that on purpose. I'm mean like that, but it shows you something that you're kind of glossing over as you read it. All right, from there, when can we determine whether or not the acceleration is 0? If no change is happening in the motion. So if it's not speeding up, slowing down, or changing direction, the acceleration is 0 by definition of what acceleration is. But sometimes there's problems where it doesn't scream that out at you. It doesn't say the thing's speeding up, slowing down, or changing direction. So you have to judge. And most of the time, it's just a judgment of whether anything interesting is happening. Like in an explosion, you expect an acceleration. If someone's been sitting somewhere for hours, no acceleration. Past that, I don't know that I have super good advice. But like, for instance, with the ramp stuff, we know the y acceleration is 0 because it's not shooting off the ramp. It's not flying into the air. It's not falling through the ground. And so nothing interesting is happening in the y direction. The x could be if it's sliding down the ramp or sliding up it. And then there are cases where they give you the forces themselves and they ask you to find the acceleration. If they're asking you to do that, then typically the acceleration is not 0. You have to solve for it. But in general, like in any problem, you can always bank on that you add this stuff up, it equals mass times x acceleration. And you could even keep going from there. You don't have to decide that it's 0 right at the time where we do. You could keep going with the problem and solve for the thing being asked for. But if you go through and you find, I don't know the acceleration, how on earth am I going to solve this problem? It's probably because it's 0 and you just missed that. So I don't know if that helps, but that's my advice on it. Re-explain the normal force on a car on a ramp. So specifically, this was from the notes. Someone asked about this. Chapter 5. All right, so I'm gonna redo some of this problem just on a new page so you can see it live. Car is parked on a ramp, and the question was about finding the normal force, but again, I don't actually care what the question's asking. I'm gonna do the same procedure pretty much no matter what. So I ask myself, what forces act on the car? Earth pulls it down. The surface keeps it from falling through. It pushes perpendicular to the surface to do that. That's the normal force. If this car were on an icy surface, it would start to slide downhill, but it doesn't. Therefore, friction says don't do that. It acts up. And I now know what kind of friction. We just called it friction in that example, but it's static friction. It's staying still. The other reason I know there must be a force up the hill is because weight has a component that points down the hill. It has these two pieces. That one is present, and if it were the only force along the hill, there's no way the car could stay still, because that force will accelerate it. It will get it moving. So there must be something to counteract that. It just turns out that that thing that must exist is the frictional force. So that's kind of inferring from the first law what's going on, that the car is at rest. Forces must be balanced. But then knowing about forces tells you specifically which one is balancing out that part of the weight. It's the frictional force. All right, so I've labeled stuff. I'm going to find components. The only problem is to find components, if they're not along an axis, you need an angle. So let me at first just pick some axes. These are convenient for this problem. And we'll do force, X and Y, friction. That's what I want. All right, start with the easy ones. Normal force only points in the Y direction, and it's in the positive Y. It has no X component. I don't need sine or cosine because the whole thing points along the Y direction. Friction, as I've drawn my axes, points in the positive X direction. It has no Y component. Weight has both X and Y components, which is why it needs sine and cosine to decide how much of the weight is in the X and how much is in the Y. But to do that, I need an angle. If this angle is given, it's the ramp angle. We've shown that this would be 90 minus whatever that angle is, and therefore this must be the angle itself, so that those two add up to 90. All right, that'll let me find my components. The Y component of the weight is adjacent to that angle, so I use cosine for it. That Y component points in the negative Y direction, and I could leave it as weight like that, but almost always we end up saying weight is mg. So I'll go ahead and do it that way. And then the X component is opposite the angle, so I use sine for it. With the axes I've chosen to draw, this is in the negative X direction, so it's a negative X component. And again of size mg, sine theta. All right, I find my net force in the X direction by adding the forces along the X. Find in the Y direction by adding forces along the Y. I just don't like negatives out front. That's just a me thing. All right, I'm guaranteed by the second law that I can set these equal to mass times acceleration. Here is where I might decide to say whether the accelerations are 0 or not, but just to touch on that thing I mentioned earlier, the question, how do you know? Well, say I didn't, and I just kept going through and solving this. I would end up, if I'm trying to find the normal force, saying Fn is, if I just move this to the other side, mg cosine theta plus mass times y acceleration. And I look at this and say, okay, well, I know the mass of the car. That was given in the problem. I know the angle theta. Again, I know the mass, g is 9.8. It didn't say anything about this one. What do I do? Sometimes we have that where we can pull another equation out of thin air and do something with the other components, but it actually, that just makes it worse, because then I'm like, well, it didn't tell me this one either. So that's where I kind of stop and evaluate, like, maybe they do tell me that in a way. And they tell me by saying the car is at rest. So the X and Y accelerations must be 0. It's not changing what it's doing. And now I can solve this. Fn is mg cosine theta without anything else added. And you put the numbers in from there. That's finishing out the problem, is whatever numbers were given. But that's the nice thing too, is like, I'm done with this problem forever. If you ever ask me, what's the normal force for a car sitting still on a ramp? It is kind of a specific question, but still I'll be like mg cosine theta. And you're like, I didn't tell you the mass of the car or the angle the ramp's at. And you say, I don't care. It's still mg cosine theta. Just put whatever numbers in you want for the specific one you're asking about. So that's the benefit of doing it all algebra-wise, is you're done with the problem for good, and you tend to make less algebra mistakes if you don't substitute in stuff at first. This question from the homework is similar. The mass of the block is given, the angle is given, and I believe it said something like it's just sitting on a ramp tied to a rope. How is it going to do much of anything else since it's tied to a rope? Can't really go much of anywhere. Okay, so that's the scenario. I don't even know what the question is. I don't care. I'm doing the same thing. Earth pulls it down. There's a surface. It keeps it from falling through that surface. There is tension on it. There's a rope attached that's pulling on it. When you pull on something, you can get static friction to oppose that pulling. But if you think about this scenario, it's not like an active pull in the same sense of if you are standing there and pulling on the rope, you're trying to get the block to slide up the ramp by pulling on the rope, there will be friction. Even if the block is not moving yet, there will be static friction on that block. But the wall is not trying to actively pull on the block. It's just a constraint on the block that it can't slide down because there's this force up the incline. But it's not like a force that's trying to do anything. And I don't think I have a more technical reason than that for why there's no friction, but there is no friction on this block. Even if it weren't a frictionless surface, as long as there's no kind of active pull happening, there wouldn't need to be friction on the block. And I think it did say it was like a frictionless incline anyway for this one. So from here, I've got my forces, and I need to turn that into a free body diagram for the block. So we've got normal force, we've got tension, we've got weight. I need to choose axes that are convenient. I will choose the one that makes me have to do the least sine and cosine type stuff. So I'll align them with the two forces that they can align with. I will pick a convenient direction for these. I'll just say X and Y. I could have drawn X the other direction. I could have even drawn Y in the other direction. It doesn't make a difference in the final answers. And I need to use this to fill in my table. In order to find the net force. Tension's along the X direction. I decided it was the positive X direction. It has no Y component. Normal force is along the Y direction, has no X component. Weight has two pieces. It is being pulled towards the ramp and down the ramp. I need an angle to be able to find those components. If this is theta, we've said it a few times, this is theta. So I will use cosine for this component because it's touching the angle, and it'll be the weight times cosine theta, so mg cosine theta in the negative direction. Over here, it will be sine theta because it's across or opposite from the angle. It's mg sine theta. And it is negative because it is in the negative x direction. So my x component is negative mg sine theta. Y is negative mg cosine theta. Bring that down to get my overall net force in the x and in the y. So the net force in the x direction is this. In the y direction is the other one. Second law says I can always set that equal to mass times acceleration. The block is just sitting there. It is stuck because this rope is keeping it from sliding down the ramp. So it has no acceleration in the x or y directions. Therefore, since the entire right-hand side is 0, when I bring mg sine theta over to the other side, it's all that's left. And then the normal force is mg cosine theta. I was given the mass of the block, I was given the angle, and finally, what was the question asking? It was asking about what is the tension, what is the normal force? Oh, I'm done. But I didn't even know. I didn't care what the question was until this very moment, and because I just turned my brain off, I did all these steps, and saw where it led me, I get the answers for free. I'm done. This is the thing I see on exams in general is you spend so much time trying to figure out the entire question that you never do the process that will lead you to it. And in that way, I don't know that it's a bad thing to try and analyze the whole thing before even starting, but it is, they call that paralysis by analysis. Nothing gets done if you spend the entire time trying to figure out how to get it done. Same goes with like projects at home, DIY stuff, and I'm guilty of this myself. I read up on how to do a certain thing for hours and hours and hours, and it's been 3 weeks and I haven't done it yet. If I would just try, I'll go ahead and break something and then fix that and then probably be done sooner than if I was just making sure I had every little detail right before I even did anything. All right, questions about friction. How do you determine when to use static versus kinetic? How do each of them apply? Static is if it's not moving, kinetic is if it is. That's pretty much it. We talked about that caveat with like when you're walking or with tires rolling, but I won't ask you one like that. But the idea there is the point that's actually in contact with the ground of, say, your feet, your entire foot, or that's in contact with the ground from the tire, that point is not sliding when you walk or when you drive. And sliding is really the thing that distinguishes static and kinetic. If it's sliding, then it is kinetic. If it is not sliding, it is static. How do each of them apply to certain scenarios? I guess the same answer. If it's sliding, you're talking kinetic. If it's not, you're talking static. In the free body diagrams, where will the friction force be placed? It is always parallel to the surface. It is always opposite the direction the thing would like to slide if friction weren't present. So this is what I do to get the direction right for friction. I pretend the thing is on ice. Which way does friction act to oppose that? And that's how I answered with the block on the ramp with the rope. Even if it were on ice, it's still tied to the rope. It doesn't need friction. If something's just sitting still on a flat surface, it doesn't need friction even if it's on ice to stay there. But if something's on a ramp and suddenly the ramp becomes icy, the block will slide down it unless friction acts up the ramp. So just make the hill icy. What's the thing going to do in that case? And then friction stops that from happening, or at least tries. For Chapter 6 notes, page 3, Part C, the kinematic equations, re-explain that. Okay, turned around on the kinematic equation I picked. So if I come back to kind of the start of the problem, it's that a car is sliding down a ramp and we are asked how far it slides before stopping. That reads like a pretty standard kinematics problem. I'm given an initial velocity. I'm given a final because it says the car must stop. So that's 0 final velocity. It asks how far would it slide. And so at this stage, I've filled in those three things in my table. I've said I'm given these two, I'm asked for this one. But every kinematic equation that you ever run across asks for three things to give you a fourth. I only have two things given to me, so I turn to these and say, do I know anything about those? It doesn't say anything about time. It doesn't say anything about acceleration either. But now that we're in the realm of Newton's laws, acceleration is like the big deal thing. So I decided maybe I can find that if I look through this problem a little bit more. And that led to this whole detailed analysis that we've kind of been through. But it ultimately got me the acceleration. That was kind of the important takeaway of doing all of that analysis was I wanted a fourth thing for my kinematics problem. And this gave it to me. It let me fill that in my table. And now I'm back to a standard kinematics problem. So I have to ask myself, which kinematic equation has these three things and would allow me to find a fourth? Or the easier way is which kinematic equation does not have time in it? And it is this one right here. It's the only one of those five that does not have time in it. And if I solve it for that distance x, which I would do by subtracting v0x squared to both sides to get it off of this side, and then divide both sides by 2 times ax to get that off of this side, so I'm only left with x. that is how I find that overall distance. Problems like 29 and 30 on the practice exam, specifically 29. Questions like that are trickier because the idea is you have to decide whether the block's going to slide at all first to know whether you're dealing with static or kinetic friction. The way in which you do that, and this is what you see in that solutions manual thing, is you calculate what is the most static friction that you could get. What is the maximum static friction? If the thing trying to make the block move is bigger than that, the block will move, and so you don't have static friction, you have kinetic. If the thing trying to make the block move is smaller than that maximum static friction force, the thing will not move, and the friction is static. And then if you're pulling at just the right size force, the right strength of force, you will match up with that maximum static frictional force, and that would be where the block is on the verge of sliding, on the cusp of doing so. It is the dividing line. That's the philosophy of questions 28 and 29 in the practice. 30, I will do a little bit more of a detailed one because I definitely could ask one like this. Hint, hint. Okay, so 30, stuntman's being pulled along a rough road at constant velocity. Sure, a similar one is like a dog sled, which I don't know how to draw, I'm realizing. Something like that, and the dude stands on it. All right, and he's got his team of dogs, which I'm not even going to attempt. They're going to be some bricks. Something like that, and a similar question to the one asked would be, a guy on a dog sled is being pulled along at constant velocity by a cable attached to a moving truck. So it'd be like ropes on the dogs are what's pulling the sled along. Let's say the cables or the ropes are parallel to the ground to make the problem a little easier. The mass of the stuntman is 100 kilograms. The parallel here would be the mass of the sled plus the guy on it. I would consider that probably is the most reasonable system because it's all moving together. And the coefficient of kinetic friction between, in this case, it would be like the snow and the sled, is some number. Find the tension in the cables the dogs are pulling the sled with. All right, so what forces are on this sled? If I were concerned about the sled independent of the guy, I would say guy is maybe putting his hands on the sled, so he's pushing this way. The sled keeps him from falling through the handles. And same here, the sled keeps him from falling through it, so he's pushing down on the sled. But those are all, if we consider this entire grouping of things as our system, those don't matter for its motion. Only external things matter. So I will consider it that way. The object under consideration is actually both him and the sled together. So this is my system. And technically that is actually the first step of any Newton's law problems. You have to define your system. It's just that you've so far mostly seen problems where there is only one kind of clear choice. All right, so I ask about the forces on this system. Well, and they must be the external forces. There's the tension could be the net tension force from both ropes, or just there's only one rope pulling, something along those lines. There's the weight of the sled, acts straight down. There is the fact that the ground keeps him from falling through it, so there's a normal force on him. I guess I should say the combination of him and the sled. And then the sled is sliding to the right, so if there is any friction, it would be to the left in this picture because the whole sled is sliding to the right, and it would be kinetic friction because the sled is sliding. It is not sitting there. It also doesn't have wheels on it that would be rolling, which would be static friction. All right, and a similar question to the one asked in the review thing would be what's the tension, but I could ask a question about what's the frictional force. And I have kind of two options there. I could either say, well, frictional force is always like this, always coefficient times normal force, because normal force and weight are the only two things in the vertical direction. They must balance out. So I could write coefficient times weight, but that's not always true. This and this are not equal 1,000% of the time. They only are here because they're balancing each other out. If there was anything else going on in the vertical direction, someone threw a rock at the top of the sled, that will change the balance of forces, and normal force will not equal mg. But in this scenario, it does. And so if I knew all of these things, I would just calculate the frictional force that way. Or it might be they tell me about the acceleration of the sled, and they tell me about the tension. Well, I can say you got tension to the right, kinetic friction to the left. That determines the x acceleration. Therefore, if I solve that for the kinetic frictional force, tension minus mass times x acceleration. But this is another scenario where if I do all the steps leading up to this point the same as I always do, free body diagram, components, and all that, I just kind of shortcutted it here, these answers fall out for you. You just have to decide what goes where in your final algebra. I'll fill in the gaps a little bit. So force, x, y, tension, normal force, weight, kinetic, find the net force. Tension is to the right. So positive x, if I'm deciding that the right is positive direction, doesn't point up. Normal force is up, doesn't point to the right. Weight is down, doesn't point left or right. Kinetic friction is to the left, doesn't point up or down. So the net force in the x direction is that. The net force in the y direction is this. Second law says I can always set this one equal to mass times x, this to mass times y. What's the sled doing? Well, it's definitely not leaving the ground. It's sliding along it, so the y acceleration is 0. I solve this for normal force. It's equal to weight. That's the thing I was talking about up here. It happened because of the balancing of forces going on. It's not true always. And then in the x direction, I got what I wrote up here. I've just done this so many times that I don't need all the in-between steps, but again, I'm encouraging you to do them as you still continue to get used to this process. To finish out, if the question was about finding tension, I take this, I solve for the tension, and I say, well, do I know mass? Depends on how the problem's stated. Do I know acceleration? Same deal. For friction, usually they give you coefficients. So coefficient times normal force. And you say, well, do I know the normal force? Yes, because you did the analysis in the y direction already. If you do get stuck here and you hadn't done it, this would just be your clue to maybe try and see what's going on in the y direction. We found it's equal to mg in this scenario. And so, assuming we had all these values, we would be able to solve this problem. And physics questions are always structured to where pretty much you do. 18. Do some questions on the max velocity for something to fall off a circular incline without friction. So that's like what we did today. So here's my car. Gravity pulls it down. The surface keeps it from falling through. And if we did want to say what friction's up to in this problem, we would have to ask, what is the car doing? Is it going a little too fast? Is it going a little too slow? If it's going a little too fast, it's going to start to skid towards the outside of the turn. So it will feel a force opposing that. And this would be kinetic friction if it is actually skidding towards the outside. If it's going too slow, it would start to skid towards the inside of the turn. And friction opposes that. So it would be this way. To account for that in actual free body diagram stuff and the components and so on and so forth, it ends up being that you'll have something that looks like plus or minus Fk. You can cover both cases at once if you use this to say, could be either, but I'm not going to ask one like that. So I'll come back to a frictionless surface, in which case these are the only two forces acting on the car. So I need to choose my axes, and this did lead to another question, which is a good one I kind of glossed over. Two good questions, actually. In the notes, the axes are chosen like this. The first question I'll address is, why were they not chosen the way we're used to, where the positive x direction is to the right? Why did they say to the left here? The answer to that is it does not matter, and I'm going to show it to you. So we'll imagine two worlds, one in which the positive x direction is to the left, and one in which it is to the right. In either case, normal force has components that are in the y direction and in the x direction. In either case, if this angle is theta, going through a little bit of geometry, this angle must also be theta. I'm ready to make a free body diagram. So here's the car, here's the normal force, here's the weight. And again, depending on which world I decide to live in today, I would choose my axes either like this or the other way. Or even I could have chosen positive y is down today. That also does not cause problems, but I'll leave that as a proof to the reader. So anyway, whichever ones I choose, it's time to start labeling my components. All right, for the left universe that I live in, I say positive x direction is to the left. Well, in that case, the x component of the normal force, since it's to the left, is positive. In this other universe, the right universe, the normal force is still to the left, that x component of it, and in this universe, that's considered negative. The weight is still 0 in the x, negative in the y. 0 in the x, negative in the y, so nothing different there. And then for the components of the normal force to decide which is sine and cosine, in either picture, the y component is adjacent to the angle, so I would use cosine for y. The x component is opposite, so I use sine. In either case, I did decide the positive y direction is upward, so I would call these positive. All right, so the only difference thus far is that sign right there. Let's keep going, see if that really causes any issues. So in the x direction, the net force is Fn sine theta. In this universe, in this one, it's negative Fn sine theta. And the y direction is whatever it is. I'm going to focus in on this part, though. I'm going to keep going with this for a second. In either case, second law guarantees that I can set that equal to mass times x acceleration. And this is where I ask, what kind of acceleration are we talking about? The answer is centripetal. The car is taking a turn, and in the diagram that's in the notes, that turn is towards the left. Because you saw that sort of that backdrop is the rest of whatever's back here. You're seeing the rest of the road. The road veers towards the left. That's the direction they're turning. If you're turning to the left, which way are you accelerating? Towards the center of that turn, which would also be to the left. And that's true in either universe because the actual scenario has not changed, just the axes we're choosing to analyze it, which the universe does not care at all about the axes you pick. Why would it? that acceleration is to the left. In the world where I call that the positive direction, this is mass times positive v squared over r, since it's centripetal. In the world where the positive direction is to the right, and acceleration to the left is considered negative. All right, so I've got Fn sine theta equals mv squared over r, and negative Fn sine theta equals negative mv squared over r. Negatives cancel. Oh, it's the same equation. And from there, all the math is the same from there on out. So I will end up with the same result we ended up with in class for that speed. For the velocity, how I choose to label that speed, that can differ depending on the system I'm in. Although in this scenario, actually the velocity is in the, I guess, the z direction. It's into the page because the car is actually moving that way at this moment in time. But you can get a sign difference, for instance, in like the acceleration itself. We saw it could be a positive or negative number. But that's because acceleration in total is a vector quantity. Its direction does matter, but the way in which we describe that direction just depends on what axes we choose. If we choose the left to be the positive direction, we would call it a positive acceleration. If we choose left to be the negative, we would call it a negative acceleration. That has no influence on the actual physical behavior of the system, just on how we label things. All right, and if I come back over here, if we choose the positive, yep, so we just did that. When would it be more useful to change the axes so the positive x direction is to the left, or can I just always keep it to the right? You can always keep it to the right if you would like. If you like that better, which personally I do typically, feel free, and then you will just have some extra negatives flying around if something is turning to the left, or if it's accelerating to the left in some way. Why didn't you rotate the axes on the banked curve problem? So the normal force was the y-axis. Very good question, very good observation. I did gloss over that too. The reason I chose my axes this way instead of you were asking about why didn't I do it the usual way we have for ramps, and it's because if I did that, this acceleration would have components in the x and y directions. And I would be dealing with an mv squared over r cosine theta, depending on what angle I'm kind of talking about it in terms of, and mv squared over r sine theta. And then weight would have components. And in some cases, the fact that you can automatically throw out one of the two, in this case we threw out ay, it's gonna be 0 in the y direction, is actually what lets you solve the problem. So picking your axes appropriately for the problem can let you actually solve it based on the information you have available, but that's just because the numbers are sort of suited for a particular set of axes, not because nature cares in any way that the axes are what they are. So long story short to that question, I chose the axes the way I did, which is straight up and down, because the centripetal acceleration is to the left. It's not down the ramp. If we had, the only thing I can picture where this would really show up, I guess, is like you had a really tilted sort of roadway the whole way around, and the center of the turn is not actually to your left, it's here, which would be like a Mario Kart kind of track, not a real thing. In that case, your acceleration would actually be directed down the ramp because that would be towards the center of the turn. All right, I think that's, I guess I'll leave it. That's a lot of that. General steps for solving any circular motion problem. Your steps are do the usual Newton's laws stuff. Which means figure out what forces are acting, put them on a free body diagram, find your components, use the second law to say equal to mass times acceleration. I know it feels like we never really bring up the first law. It's because it's sort of like a special case of the second law almost. It says what happens when specifically AX and AY are 0. The reason you need it as an independent law from the second is 1, because we just developed it first, and then second came later. 2, because it confirms what happens at 0 acceleration rather than it just being us sort of following the trend and saying, I know this equation works when AX is not 0. Am I for sure certain that it's true when AX is 0 or when on this side the net force is 0? And what I mean by that is not whether the mathematical stuff, the statement is true, but is that true in reality? So Newton's first law is about saying, yes, actually, if there's no force, no acceleration happens in reality, not just because the math feels like it should be. Okay, but anyway, that step is actually what comes after that second law, is not that they're 0, but you decide on the acceleration. So decide if any are 0, or if they're given, you use that, or if it is centripetal. That's where the v squared over r comes up. Depending on which way the acceleration is, are they turning to the left, are they turning to the right, and how you've defined your axes, that will be a positive or a negative value. And then the last step is solve for whatever, doesn't matter. These steps run about the same no matter what the problem is. There's little minor differences depending on the types of forces you're talking about, but the actual procedure is the same. Down for these last two, that's where you end up having to be a little bit more sort of creative. You turn your brain back on and decide, like, what's true about this scenario? And that can include things like remembering that weight is mg, or that the maximum static friction is coefficient times normal force, or that kinetic looks the same but with a different coefficient. Or, again, kind of bringing in that centripetal stuff. Or for other forces, like we will talk about springs later, there's other what you call constitutive relations, which is just saying what contributes to this force, what does it care about? For a spring, it cares how much it was stretched, that's x, and then what it's made of, that determines the spring constant. All right, so that's your general procedure. Are there any common mistakes you have seen people make on this exam in the past? Oh, absolutely. The biggest one is not following this general procedure that we've done a dozen times at this point, and I've like painstakingly tried to say, look, it's the same process. Please just do it. I beg you. Fill in your table. Draw your free body diagram. Go through these steps. Don't try and eat the whole problem at once and spit out an answer, because it's not going to go well. If you turn your brain off for the first 3/4 of the problem and just do the steps, the answer falls out for you at the end. As you get more experienced with that process, someday you can shortcut it, and that is doing what you wanted to do in the first place, which is answer the whole question at once. You develop the intuition to be able to do that, but that does not come immediately, and it does not come quickly. The way to do it is to be in the trenches doing all the component stuff until someday it all just clicks and you're like, I'm doing the same thing every time, aren't I? Okay, so other than that, mistakes include directions of forces on the free body diagram. Just remember normal force is perpendicular to the surface. It is not up on a ramp. I see that a lot. That is not correct. Normal force is not always equal to mg. As much as you would like it to be, it's not one like the list I wrote over here. It's not a gimme. It is one you have to show using that same process. You go through what's happening in the y direction, typically the normal force is in the y, but whatever axes you chose, and you see what it must equal based on what else is going on around it. because that's what you call them constraint forces. That's what they do, is like the normal force is whatever it needs to be to keep the car from falling through the road. A table, the normal force it provides is whatever it needs to be to keep you from falling through. If you keep putting stuff on that table, the normal force will grow to try and keep it from falling through. What happens eventually is sort of like what we saw for friction. You have a breakaway point. But in this case, it switches over from there is a table to there isn't because it broke. So normal force just sort of keeps up that way. Tension, same deal. It keeps up to a point. There's a breakaway point at which you switch over from there is a rope pulling on something to there isn't because it snapped. But we deal with problems in this class, at least, at the level of stuff doesn't break. You just have a switch over from static to kinetic friction, for instance. Reason for that is stuff breaking is actually horribly complicated. You'll talk about it in mechanics of deformable solids, I think is the course, or fracture mechanics, or you may never talk about it at all. I don't know. But the math there is horrendous. Yeah, you don't want it unless you really need to know about the fracturing of stuff. It uses stuff like hypersingular integral equations. It uses, I saw some stuff pop up in my graduate research, Hadamard finite part, Cauchy principal value stuff, fractional calculus. The tools are ridiculous in that area of study, even for like formation of cracks on things. But that's another tangent. It's just if you wanted to know, there you go. All right, and finally, I suppose coming into this exam thinking you're not going to need to know how to draw a free body diagram, because I do ask on every question, or I say like full credit for this question requires you draw a free body diagram. You're not allowed to not do it if you want the full points. And mixing up velocity and acceleration for stuff moving in a circle. That's another one. If you're spinning something around on a string, say you're spinning it this way if you're looking down overhead, velocity is which way it's going at each moment. And it's going to be tangent to the circle. Acceleration is what keeps yanking it back onto the circle. The ball wants to keep going if we're talking about up here. It would love to keep going this way. Its inertia says, do that. What doesn't allow it to is a centripetal acceleration, a yank back towards the center of the circle to say, no, you're going to keep going on the circle. And then over here, it would love to keep going that way, but then there's a yank back towards the center that says, you're going to keep going this way or along the circle. Where does that yank come from? Whatever is providing the centripetal force, the rope, the friction, the gravity, whatever it is. But anyway, that means the acceleration, the way in which the velocity is changing is it gets yanked towards the center. Literally think of to get from this direction of velocity to what it is slightly later in the circle, you have to take it and twist it towards the center of the circle to get this new vector. That's the role of the acceleration, is it's telling the velocity what to do next. And so it's always towards the center of the circle, always saying, go that way, go that way, go that way. And same goes for the centripetal force. It is what's making that acceleration happen. It is the pull that's actually causing it that says, go that way, go that way, go that way. So anyway, cleaner figure. Velocity is always tangent. Acceleration is always towards the center. And they are always perpendicular to each other if all the thing is doing is turning. If it's speeding up or slowing down, that's not the case anymore, but we haven't covered that yet. One more. Sine versus cosine, when do you use them? The cop-out answer is go back to chapter 3 and look at how we found components of vectors in general. The idea is just if, for whatever angle you have to work with, the component you drew is adjacent to it, you'll use cosine. If, for whatever angle you were given to work with, the component is opposite it, use sine. So say this vector right here, if I have my axes like this, and I'm given this angle, and then I would probably draw my components like this, so that they sort of encapsulate the angle. If I had drawn the components the other way, the angle wouldn't be part of the triangle I drew. If I do have this angle to work with, call it theta, and let's say this is just called vector A, this would be A cosine theta, because it's touching the angle, it's adjacent to it. This is A sine theta. All right, what if I was given this other angle? I'll call it phi, just so it's a different kind of variable name. In that case, because to get to the x component, I got to go across, the x component is A sine phi. If I'm talking about the y component, it's touching that angle phi. So A cosine phi. And so even though these two actually represent the exact same length, I use cosine if I'm dealing with this kind of angle. I use sine if I'm dealing with this kind. But it's not, don't even, you're thinking it's x and y now. It's not. The only rule is adjacent you use cosine, opposite you use sine. There is no other thing to it. It just becomes, it's just the skill of being able to do that immediately. Recognizing adjacent versus opposite, and really being able to draw in your components. That's another one that I think is not fully fleshed out sometimes by this exam, is like, do you know what components are? They're to tell me how much of this vector, whatever it may be, a force, a displacement, whatever, how much of it points up and down, how much of it points left or right, or along whatever axes you're dealing with. It's just splitting a vector into pieces that fit along an axis. And that reminds me, I think I did have one more email that I think I forgot to put the questions in my list for. For the car engine question in Chapter 5 notes, how do we determine which angle to use for each type of component? All right, so that's good because it's a specific example we can look at of this. Why is it that I used the 80 and then the 10? Because that's what I was given to work with. And I'm used to drawing components enough that it doesn't faze me if I have an angle that's given in a weird quote unquote way, because it's not weird to me anymore. So I just work with the angle I've got. They gave me this one, so I draw my components to encapsulate it. If I had drawn them this way, to the left and then up, I wouldn't have that angle inside. But even that wouldn't faze me. I'd be like, oh, okay, well, that's fine. This is 80 degrees. In which case, the x component I would use cosine for, because it's adjacent. The y component I would use sine for, because it's opposite the 80-degree angle. But when I did it this first time in class, I used the 10-degree angle, in which case the x component I used sine, because it's opposite 10, and the y component I used cosine, because it's adjacent to that 10-degree angle. And this is true even if you had some bizarre kind of axes, like if you found out that this angle was like 50 degrees, and for some reason you needed to know how much of that force was along this axis versus that axis, also fine. It's the same process. You just say how much of the vector is along each of those axes. And that's kind of what we have to do for something on a ramp. It is sort of odd axes like that, but it doesn't cause issues if you know that it's just that adjacent is cosine, opposite is sine. If you are stuck in the world of x is cosine, y is sine, because that's not correct, that's not the rule, you will get lost if we do weird axes or give the angle in not the way that you like. So that's why I'm trying to break the habit. It's not that x is always cosine, y is always sine. It's that adjacent is always cosine, opposite is always sine. When can we determine whether or not the accelerations are zero in the context of problems? I addressed that, but this was a specific one. So Chapter 6, dry versus icy. Okay, so I think the question is, why did I know this one was zero, but this one was not? The y was zero because the car is not hopping. It's not doing anything interesting in the vertical direction. That one is like, I don't have a forever rule for you other than just acceleration means the velocity changed somehow in that direction. The car wasn't moving up or down at first. It's still not going to be moving up or down a little bit later. if it's just following a flat road. In the x direction, I ask what the car is doing. It was facing in one direction at first, and then it's facing in the other. Like if we're talking about the car taking a turn, the direction it's facing is changing. And so if I tried to draw this free body diagram at a later time, my x-axis would actually have sort of pivoted and pivoted and pivoted to keep pointing towards the center. So something definitely is happening in the x direction. Something is changing in that way. And so I have to ask, what's the change that's happening? Are we speeding up in that direction? No. Are we slowing down? No. But there is this one final possibility. Are we turning around an axis that is off to the side so that the x-axis is sort of pivoting around it? Yes. We have a centripetal acceleration in the x direction. Therefore, I can't say it's 0. I have to use the centripetal acceleration expression. So I guess just ask, like, is what the car is doing changing from one moment to the next as far as how it moves? If yes, there is an acceleration in that direction. If no, then there is not. All right, I think that is it, if anyone made it this far. If you did, the answer to the bonus will be B. All right, we'll see you on Tuesday. Have a good day.